So, think about this. You can stick a piece of tape to almost anything, right?
Yeah.
That seemingly simple act, that little bond, and even the way water beads up on a raincoat,
Uh-huh.
these everyday things, they actually hint at this hidden world of tiny, tiny forces.
Absolutely. Force is so fundamental. They govern everything from how geckos climb walls to, believe it or not, how our own DNA holds together.
And the story behind understanding these forces. Wow, that's what we're getting into today.
Exactly. We're doing a deep dive into the life and work of Johannes Diderik van der Waals. He was a 19th century Dutch physicist.
Right.
And his journey, I mean, it's full of twists and just this incredible dedication. It really changed how we understand matter.
So our mission here is to figure out how this one person, facing, some serious headwinds, personally and scientifically,
Peak time.
how he dared to challenge what everyone just accepted back then. And for you, the learner listening in, this is a great chance to see how science breakthroughs aren't always like a straight line.
No, definitely not. It's often about grit, perseverance, refusing to just accept the limits people put on things.
Okay, so let's start at the beginning. You mentioned headwinds. Talk about his early life. It sounds like a real uphill battle.
Yeah, let's set the scene. Imagine this bright kid, really curious about science, wants to dive into physics in the Netherlands. But, there's this huge barrier.
And it wasn't that he wasn't smart enough or interested, right? It
Yeah,
was language.
Exactly. Language. Back in the 19th century, if you wanted to go to university in the Netherlands, especially for something like physics, you absolutely had to know classical languages, Latin, Greek.
Seriously? For physics?
Yep. And van der Waals, well, his background didn't include that kind of classical training. So basically, the door to the usual academic path was slammed shut.
Wow.
It's kind of like, imagine a brilliant programmer today who can't get a job because they never learned cursive. It seems unrelated, but it was the rule.
That must have been so frustrating. You have the drive, the smarts, but you're blocked by Latin.
You can imagine. But what's really impressive is what he did next. He didn't just give up.
Right, he found another way. Resourceful.
Totally. He became a school teacher. That let him keep learning. And crucially, he started unofficially attending physics lectures whenever he could squeeze them in.
So he was basically piecing together his education on the side.
Pretty much.
Right.
Just sheer determination, absorbing knowledge, because he was so driven to understand how the world worked.
That's amazing dedication. And then eventually things changed, those language rules.
Yeah, luckily for him, those requirements were eventually eased. And when that door finally opened, boom, he grabbed the chance, finished his degree really quickly.
Shows what happens when you remove those kinds of arbitrary barriers.
It really does. And that whole experience at Resilience, it was probably vital for what came next, when he started tackling the really big questions in physics.
Okay, so let's move to that. The late 1800s. It's kind of wild to think that the very idea of molecules wasn't like a settled fact back then.
It's hard for us to wrap our heads around now, isn't it? But yeah, prominent scientists, big names like Ernst Mach, Wilhelm Ostwald, they were really skeptical about molecules.
Why, though? What was the objection?
Oh, you couldn't see them, right? So for some, it felt a bit like hand-waving, explaining something mysterious with another unseen mystery. They preferred theories based strictly on what you could directly measure.
Okay. So into that skeptical environment, here comes van der Waals with his PhD thesis in 1873. That sounds like throwing down a gauntlet.
Oh, it was absolutely revolutionary. His thesis basically said, look, real gases don't follow the ideal gas laws perfectly because the particles they're made of molecules actually attract each other a bit. And also, these molecules take up space. They aren't just zero volume points like the ideal gas theory assumed.
So he's directly challenging the standard model by saying these invisible things do have properties that matter.
Exactly. He wasn't just tweaking the old laws. He was introducing these two crucial new factors based on the reality of molecules.
And that leads to his famous equation, the van der Waals equation. How did he capture those ideas mathematically?
Well, his equation specifically added terms to account for that intermolecular attraction, sort of a stickiness factor, and the actual volume the molecules occupy.
Okay.
And the really elegant part was his equation hinted that gases and liquids weren't fundamentally different things. They were just different states of the same molecular system.
Whoa, so connecting gases and liquids through these molecules nobody was even sure about.
Precisely. It provided a theoretical bridge based on the behavior of these debated molecules. A huge conceptual leap.
I bet that didn't go over smoothly with everyone.
Not at all.
Yeah.
Initially, a lot of skepticism, a lot of resistance. It's never easy challenging the way things have always been understood.
Yeah.
You have to imagine how isolating that might feel. Putting forward this big idea and having many of your peers kind of dismiss it.
So he's this lone visionary, sticking to his ideas. What kept him pushing? How did he fight that skepticism?
Well, partly just deep conviction in his theory. But crucially, he backed it up with data. Rigorously.
Ah, the evidence.
Exactly. He didn't just publish the equation and walk away. He spent ages meticulously comparing its predictions to actual experimental measurements for all sorts of different gases, under different pressures, different temperatures.
So grinding it out, showing it worked in the real world.
Yes. That painstaking work demonstrating again and again that his equation actually described reality better than the old ones. That's what gradually started to shift opinions. It made the existence of molecules and these forces between them much harder to deny.
And eventually that persistence led to the ultimate recognition, right? The Nobel Prize in 1910.
Absolutely. A massive validation, of course.
Must have felt good.
I'd imagine so. But even beyond the prize, the impact was immense. His work on intermolecular forces, it opened the door to studying what happens at really, really low temperatures.
Like near absolute zero.
Exactly. It paved the way for cryogenics, understanding things like superconductivity. Whole new fields of research bloomed because of his insights.
And that brings us right back to where we started, the get-go, the water droplet.
Right back.
Yeah.
Those very forces he theorized about, the ones we now call van der Waals forces, they're the reason for those things.
So it's these weak attractions, but lots of them adding up.
Precisely. Individually, they're tiny.
Yeah.
But you get countless molecules interacting, like on a gecko's foot with all those microscopic hairs.
Uh-huh.
And the collective effect is strong enough to let it cling to a wall. Same with water. The attraction between water molecules creates surface tension, makes beads form.
And even DNA.
Yep. These forces play a critical role in holding the strands of the double helix in their specific shape. It's kind of amazing how his abstract theoretical work connects to all these tangible things.
It really is. It ties everything together. You know, the material we looked at used these metaphors. The river and the rock.
Yeah, I like that. Van der Waals as the persistent river, slowly wearing down the rock of established scientific thinking.
It's a powerful image.
It is, and it makes you think, doesn't it, about the stones, the obstacles we all run into.
Mm-hmm.
And it sort of encourages you to find that river inside yourself, that determination to push through.
Yeah, it makes the scientific struggle feel very human, relatable, not just equations on a page.
Exactly. His story really goes beyond just physics. It's about, well, the human spirit, isn't it? Persevering, questioning assumptions, believing in your vision, even when everyone else doubts you.
And wasn't there another famous scientist who saw his potential early on? Maxwell.
Yes. James Clerk Maxwell, a giant in physics himself, apparently read Van der Waals' thesis and recognized its significance almost immediately, predicting he'd be important.
Wow. That shows that sometimes, even if the mainstream is skeptical, a truly groundbreaking idea can resonate.
It does. It suggests that fundamental insights, even if they take time, eventually get recognized.
So, if we boil it down, the big takeaway here is that the edges of what we know, they aren't fixed, are they?
Not at all. They're constantly being pushed, redrawn by people like Van der Waals who dare to think differently and just keep going.
His life really shows that progress often depends on that courage, to challenge things and stick with an unconventional idea.
Definitely. Tenacity is key.
So maybe for you listening, as you think about the challenges or the walls you might be facing, maybe take a page from Van der Waals. How can you find creative ways to, well, climb over them?
Yeah. We hope this inspires you to dare to see what others might overlook, dare to keep going when things get tough or when people doubt you.
And dare to believe that your own efforts, even if they feel small sometimes, can actually make a difference. They can change things.